Hi, welcome to Chem with Chem. This is the full work through of the CSEC Chemistry Paper 2 from the June 2019 sitting. Please like, share, and consider subscribing so you don't miss out on any of the content posted on this channel. There are several links in the description section below this video which take you to other full and partial work through as well as experiments. For your viewing pleasure, use the timestamps to toggle to your favorite or desired question. Have fun. Now, question 1 is a data analysis question, as is customary, and we're being recommended not to spend more than 30 minutes on this question. Now, this one is a mouthful, so let's just zone in and get everything clear. Let's just get in and just see how best we can understand, interpret, and just get full marks. Michael and Jennifer were assigned a group project to investigate the effect of surface area on the rate of reaction between zinc metal and the dilute sulfuric acid. And this is becoming, I don't want to say we're seeing a pattern, but we tend to get these types of questions for number 1. You know, it's a lot of titration or rates of reaction, but they tend to mirror experiments that would carry out in the lab. So they obtained 6 different grades of granulated zinc. The grades represent the average size of the radius in microns, micrometer, of the granules. 6 experiments were carried out using the different grades of zinc granules, which were reacted with an excess of 0.5 moles per dm cube dilute sulfuric acid at 25 degrees Celsius. Very important. So temperature is held constant and excess acid is used to ensure that all the zinc granules is used up. The same mass, very important, the same mass, 0.55 grams of zinc granules was used in all experiments, and the time taken to collect 100 centimeters cube of hydrogen gas was noted as shown in table 1 on page 6. So we're not going to directly go to table 1 on page 6, all right? Just for ease of scrolling, we're going to just go straight into recording the readings that are shown on the stopwatch. So in question 1, a data analysis question, we're always given some instruments with gradation that we'll have to find out the scale and we'll have to do some reading. So we're just going to make a note of that. So when we go to page 6, we can just fill in the values and just do whatever calculations are required there regarding the rate. All right. So we're going to make a note of the time taken in each experiment. All right. So firstly, we always figure out the scale on whatever instrument we're using. So in this case, each of these little strokes that we see, they're representing 1 second, right? So it's a 1 minute stopwatch. Each of them is representing a second. So it means therefore that what we have here for experiment 1 is 11 seconds, 11.0 seconds, right? Experiment 2, that would be 20 seconds, 20.0 seconds. Experiment 3, that would be 30, 31, 32.0 seconds. Experiment 4 would be 43.5 seconds. If you have 43, you should still get the mark. Experiment 5, 52.0 seconds, and experiment 6, 58.5 seconds. So we're going to take those and we're going to put them in our table, which comes next. But just for ease of scrolling, we're doing our readings right now. So table 1, this is the data obtained for experiments 1 to 6. Part 1, from the stopwatches displayed in figure 1 on page 5, record the times for the hydrogen gas to be collected in column 3 in table 1. The time taken for experiment 1 has already been recorded for you. So we're just going to fill in our table. So we have 20.0, 32.0, 43.5 for experiment 4, experiment 5, 52.0, experiment 6, 58.5. And we're not doing this in a vacuum. I would like us to look at the diameter, sorry, the radius of the zinc grade that we're using. So we realize that so in experiment 1, we had zinc granules with 0.8 microns, and they kept on increasing. Experiment 2, 1.9, experiment 3, 3.0. So the radius was getting larger and larger. So this is telling us that, well, we know, well, I shouldn't say we know. The larger the radius, then it's telling us that the surface area is smaller. So the smaller the radius, the larger the surface area. Just need to bear that in mind. Smaller particles have larger surface area. So let's look at the time now. So for the one with the smallest radius of 0.8, we notice that it took 11 seconds for 100 cm cube of gas to be formed. Let's compare that with the one with the largest radius, which would have the smallest surface area. 6.3 microns, that one took all of 58.5 seconds. So it took longer. So the larger the radius, the smaller the surface area. In a sense, we're saying the smaller the surface area, the slower the rate of reaction, or the smaller the surface area, the more time it takes for the 100 centimeters cube of gas to be formed. So that was part 1, and we got 3 marks just now. Part 2, using the formula rate is equal to 1 over time, calculate the rate of reaction for each experiment and record these values to 3 decimal places in column 4 of table 1. The rate of reaction for experiment 1 has already been calculated for you. So we're just going to say 1 divided by whatever the time is. So in experiment 2, it's 1 divided by 20, which will give us 0.050. It's at 3 decimal places. And then 1 divided by 32, that would be 0.031. Then there is 1 divided by 43.5, 0.024. Then 1 divided by 52, 0.019. And then there's 1 divided by 58.5, which will give us 0.017. And 3 more marks. So in the next question, we're going to be plotting a graph of the rates. So all that we have in column 4, rates of reaction versus the time. So rates will be on the y-axis and time will be on the x-axis. So that's what we're going to be doing next. So make a note of these values, have them ready so we can plot in the next question. So in part 3, using the grid provided on page 7, plot a graph of rate versus time for experiments 1 to 6. Draw the best curve through the points. What's very important when we're going to plot, or before we even plot, is that we determine the scale that is being used on the x and the y-axis. So on the y-axis, we're seeing that 2 centimeters are being used. So the scale, we're seeing that 2 cm, 2 centimeters are being used to represent 0.01 units, right? So it means that each of the little millimeter boxes that we have there, each of them is representing 0.001. All right, so each of them will be going up by 0.001. All right, on the x-axis, we have the scale on the x-axis, we'll have 2 centimeters representing 10 units. It's been used to represent 10 10 seconds. So it means each of the little boxes there, the millimeter box is going to be used to represent 1 second. So it's a little easier. And in the interest of time, I've gone ahead and I've plotted the points. So for 11, we'd find 11 seconds on the x-axis and would come up and we'd look for the rate that corresponds with 11 seconds. So that would be 0.091, and that's plotted. We do the same thing, 20.05, 20 seconds, 0.05, then 32.031, and so on. The next thing we would need to do is to draw the best fit, the best curve. And the best curve will go through most of the points. Sometimes we'll go through all of them. Other times it will not go through all of them. So we want to do the best curve, and it should be smooth. We want to do it in one go. So here we go. So that's what your best curve would look like. Mine is a little wiggly in some areas, not as smooth based on the device that I'm using. So that would give us the full marks there. We can just look to see what is happening here. We're seeing that as time increases, as you go across on the x-axis, you see where the rate is decreasing. And more than likely, we should expect a question like this, because there's normally a question asking us to interpret the graph to see what the trend is. So as you go across on the x-axis, you're seeing that the rate is decreasing. The rate is decreasing, all right? And we can put that into better perspective. If we were to go back to the table we had with the zinc grade, we're finding that the smaller the radius of the zinc grade, the faster the rate, or the shorter the time it took for the 100 centimeters cube of gas, to be formed, or just the smaller the radius, the faster the rate. And the smaller the radius, the larger the surface area. That's the link that I think I had mentioned earlier. B, part 1, based on the graph plotted on page 7, deduce how the rate of the reaction varied with time. So we'll say it simply, as time progresses, as time progresses, the rate of the reaction slows down, or we could say the rate of reaction decreases as time progresses. I don't fancy this question at all. Anyway, moving right along. Part 2, explain how the trend in the rate of reaction stated in B1 relates to the surface area of the zinc granules. So this trend that we saw in B1, we looked at the graph earlier, it's directly related to the surface area. So we have to make it clear though that the smaller the radius, the larger the surface area. We probably don't have to state it here, but we can just get straight to the point. So for 2 marks, the larger the surface area, the faster the rate of reaction. The larger the surface area, the less time it took for the reaction to be completed. So All right, so the larger the surface area of the zinc granules, the faster the rate of reaction. 2 marks. Part 3 of B. List 3 factors other than surface area that affect the rate of a reaction, the rate of a reaction in general. So besides surface area, we have concentration, we have temperature, and we have the use of a catalyst. They did not say this reaction in general, they said rate of a reaction. State 1 safety precaution that Michael and Jennifer may have taken during the experiment, and it's always safe to say wear enough protective gears. PPE, right? So gloves and goggles, lab coat. D, state 1 way in which Michael and Jennifer may have controlled the temperature during the experiment. So they said this was held at 25 degrees Celsius, taken to be room temperature. They could have used a styrofoam cup, you know, an insulated system where heat would not enter or leave. So they could have used, or they may have, or they could have insulated the container in which the reaction took place. So this part is the, well, last section, E. It has 2 parts for 5 marks. Part 1, 2 marks. Part 2, 3 marks to make it up to 25. Write a balanced chemical equation including state symbols for the reaction between zinc metal and sulfuric acid. So this is Zn, which is a solid, plus H2SO4 aqueous to give zinc sulfate, ZnSO4 aqueous plus H2 gas. So just writing this as is, it's balanced, 2 marks. Part 2, calculate the total volume of hydrogen gas that would be produced at RTP from 0.55 grams of zinc granules. Okay, so this calculation is going to be governed by our balanced chemical equation. So from this balanced chemical equation, we're seeing where 1 mole of zinc, let's change color, 1 mole of zinc reacts to give us 1 mole of hydrogen gas. And we're just focusing on the hydrogen gas because the question is asking us about hydrogen gas and zinc. So let's move from moles now. 1 mole of zinc, well, the RAM of zinc is 65.4. So 1 mole of zinc has a mass of 65.4 grams. So we're saying 65.4 grams of zinc produce 24,000 cm cube of hydrogen gas at RTP. So that is going to be our first statement. And we can just take that down. So we'll say from the equation, we're saying that 65.4 grams of Zn react to give us 24,000 cm cube of H2 gas at RTP. So we want to find out if we actually used, 0.55 grams of zinc under the same conditions, what volume of gas would we end up with? So we put X right there, and it follows that we would end up with less because, you know, 0.5 is less than 65.4. So we'll just cross multiply. So we normally put on, you know, lines there to say we're going across the diagonals. So it would mean then that 65.4 grams times X is equal to 0.55 grams times 24,000 cm cubed. We want to make X the subject, so we divide by 65.4 grams on both sides. All right, and of course, we know 65.4 grams cancel out 65.4 grams. So it's a matter of punching in into our calculator now, and we write down our value. So we would end up with 0.55 times 24,000. Whatever we get divided by 65.4, and that would give us 201.8 cm cubed. And that is our answer. That would give us the remaining 3 marks to make it up to 25 marks. And just like that, 25 marks. Be sure to pause, rewind as many times as possible to ensure that you are clear with the concept. You just want to do that before you move on to question 2. If you're fine and you've grasped the concepts that are, expressed here, then be sure to move on to question 2. Table 2 lists the chemical symbols of elements in period 3 of the periodic table and their respective atomic numbers. Right, we're seeing sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, 11 to 18. Part A. Explain why these elements are all placed in period 3 of the periodic table. No, elements are arranged in the periodic table according to increasing atomic number. Yes, they're arranged in the periodic table according to chemical properties, but they're also arranged in the periodic table according to their electronic structure. And that one is broken down. We look at what number is in there, what number you have for the valence, the last number in electronic configuration, pretty much. Or you look for how many numbers you have in their electronic configuration, which is what tells you which period they're placed in. So they're placed in period 3 based on the number of shells that they have. So all these elements here, they have 3 shells. Electrons are being added to the 3rd energy level. So if we were to look at the traditional electronic configuration for sodium, for example, we will see that the electronic configuration for sodium is 281. For magnesium, it's 282. For aluminum, it's 283. Silicon, it's 284. Phosphorus, 285. Sulfur, 286. Chlorine, 287. And argon, 288. I always hope that no one is passing my class and hear me saying 282 and thinking that I'm saying the times table 282, 283, 284. But we're just talking about the electronic configuration. So there are 3 shells, so they are in period 3. So let's get that down. So these elements are in period 3 because they have 3 electron shells, or we could say the 3rd shell is being filled. Electrons are being added to the 3rd shell. Which element, part B, which element in table 2 forms an oxide which readily dissolves in water to give a solution with a pH greater than 7? Write a balanced equation to support your answer. So pH above 7, we're talking about something that's basic. So it could work with sodium or magnesium. I'm going to work with the first one. Sodium. Is somebody saying no? Well, it's actually sodium. So sodium will work. So that will give us an alkali. And the equation, sodium reacting with water, so sodium is a solid, plus water, H2O, which is a liquid, and that will give us sodium hydroxide, which is aqueous, and hydrogen gas, that's H2 gas. And of course, we would need to balance. Let's use a different color to balance. So we need a 2 here. That makes it 4 hydrogen, yes. 2 oxygen, but probably should have explained what's happening. Well, let's go. So there's 1 sodium on the left, 1 sodium on the right. 2 hydrogens on the left, 3 hydrogens on the right. 2 can never catch up 3. So we can do some modification. We can put a 2 right here. That will change the hydrogen to 4. But we would still have 3 hydrogens on the right. So we need to put a 2 in front of the sodium to make the hydrogen that's here 2. So the total number of hydrogens now would be 4. Because the 2 here is saying everything that comes after the 2 is multiplied by 2. So it means that we have a total of 4 hydrogens now. On the right, we have 4 hydrogens as well. So hydrogens check, water, 2 each, 2 on the left, 2 on the right. This 2 in front of the sodium means that we need 2 in front of the sodium on the left to ensure that everything is in check. So that's that. Part C, the element sulfur can exist as different as allotrope. So was to an element existing in different forms. So they will have different chemical properties, but they will have different physical properties, but same chemical properties. Part D, draw a diagram to show the arrangement of electrons in sulfur. All right, so we're going to show what's in the center first. That's the nucleus, where we would have 16 protons and 16 neutrons, right? And some books will show you a shell around this or a circle around this for the nucleus. Some will put a dot in the middle. So I'm using a circle to show the nucleus. If you don't use a circle, it's fine. So I'm going to actually keep this ring right here. So this is the first shell. Sulfur is 16, so we have 16 protons, 16 electrons. So that's the first shell. Second one, we said 2, 8, 6 earlier. And remember, we pair the electrons, 2, 4, 6, 8. And then the third shell would have 1, 2, 3, 4, 5, 6. And that would give us 2 marks. E, part 1. State the type of bond that forms when sulfur reacts with chlorine. Well, sulfur is a nonmetal. Chlorine is also a nonmetal. So when nonmetals combine or when nonmetals bond, we end up with a covalent bond. So the bond is bond, covalent bond. All right, so this is a covalent bond. Co means sharing, valent, referring to the electrons in the valent shell. So there's some sharing taking place. And we answered part 2 in a sense, explain why the type of bond stated in EI is formed for all of 3 marks. So we'll state sulfur, and I spell it with a PH, sulfur and chlorine are both so sulfur and chlorine, they are nonmetals. And when nonmetals bond with each other, the bonding is covalent, sharing of the valence electrons. F. Write the formula of a compound which is formed when sulfur reacts with chlorine. Okay, so sulfur, we said earlier, it's 286. Chlorine is 287. Of course, we could just straight up write the formula, but I want us to see where it's coming from. Sulfur needs 2 to complete its octet. Chlorine needs 1. So when they share electron, sulfur will share with 2 chlorine, and we're going to look at what happens in G. So the formula would be, or if we continue, sulfur needs, let's use blue to show how many sulfur needs. Sulfur needs 2, chlorine needs 1. So the LCM of 2 and 1 is 2. 2 into 2 goes 1. 1 into 2, 2. So it tells us how many sulfur we're going to need and how many chlorine we're going to need. All right, just a little math right there. So this formula is going to be SCl2. And they want us to draw in G, draw a dot and cross diagram to show the bonding in the compound stated in F. All right, so sharing of electron is going to be taking place. So we're just going to write the symbol and we're going to use only the valence electrons. All right, so we'll need to show 6 electrons in sulfur. We know chlorine has 7. I'm using dot and cross. The electrons are identical, but we just want to show the variation so we know which one is coming from the chlorine. So chlorine, we said chlorine is 287, sulfur is 286. So when we put a chlorine beside this, using hugs and kisses, as we said earlier. So that is what we'll have. So when we're counting the electrons, in chlorine, we would count, let's look at, so this is the final thing. I'm just going to use a little, going to highlight so we see what's happening. These electrons here, these electrons are being shared. So they both belong, where we see the overlap, those electrons both belong to the chlorine and the sulfur. So sharing is taking place right there. All right, so that is that. So you can ignore the highlighted part. I just wanted to show. All right, so when you're counting, if you look around sulfur, you'd have 8 surrounding it. If you look around each chlorine atom, you'd have 8 surrounding it. So they would have a complete octet, and that is what would make them stable. The whole point of them bonding in the first place, so they can achieve noble gas configuration. And we've come to the end of this question. If there's a part for which you needed explanation or clarification in question 2, be sure to state it under the comment section. And just a gentle reminder to like, subscribe if you haven't done so, and share. Now, this question is an organic chemistry question, and it's on polymers and reactions of organic compounds. Part A. Polymerization is an important industrial process used in the manufacturing of many useful materials. 1. Define the term polymer. And this is something we would have seen before. A polymer is the compound formed when many monomer units join. distinguish between part 2, distinguish between addition polymerization and condensation polymerization. So in addition polymerization, when the monomer units join, the final product is 1. We get one continuous chain, whereas in condensation polymerization, when the monomer units join, we get the long chain compound, the polymer, and there's normally the elimination of a small molecule such as water or HCl. Part B. Figure 2 illustrates the formation of a polymer. Part 1. State the type of polymerization represented in figure 2. So let's look at the figure. Let's examine the figure and see what the repeating unit is. So our repeating unit is, we're given the repeating units. We have what looks to be a diacid compound on our left here with two COOH group, which is the functional group for carboxylic acid. So this is a diacid. And the other compound appears to be a diamine. We have two NH2 groups, which is the amine group on either side. So if we, well, no if, no buts. Whenever we have a diacid and a diamine reacting, we're going to get a condensation polymerization. We're going to actually get a polyamide, but we don't want to over answer part 1. We just want to state the type of polymerization. So the polymerization here is condensation. And they want us to give an explanation for our choice. And it goes back to our definition or our differentiation between addition and condensation. Earlier on, we had the elimination of water. And whenever we see elimination of water, it means that condensation, polymerization would have taken place. That's the whole point. Condensation having to do with the formation of water. So we can say water molecules were eliminated. So it's a condensation reaction or condensation polymerization. All right, and it's just 1 mark. We don't need to over answer. C, identify one use of each of the following types of polymers. Polyester. So polyester is used to make fabric. That is used in clothing. Polyalkene, there are so many uses. We use them to make plastic containers. Plastic containers, buckets, PVC pipes, and so on. Part D. Figure 3 shows the fully displayed structural formulae of compounds A and B. And we just want to look at compound A. We're seeing the OH group, functional group, the OH group there. In compound B, we're seeing the C double bond OH group. That's the carboxylic functional group. And they want us to, in part 1, state the homologous series to which compounds A and B belong. So whenever we see OH, we can just say, oh, and we know that we're talking about the alcohols. So compound A would belong to the alcohols, and compound B, whenever we see COOH, it means we're talking about our carboxylic acid, or what we call our alkanoic acids. And they want us to go a little further and to give the name of compound A. So we have 2 carbons present here. So the prefix we're going to use is et for 2, and we'll add the suffix or the ending name anol. So this is ethanol. And just like that, 3 marks. Part 3. Compounds A and B react to form compound C. Sketch the fully displayed structural formula for compound C. So let us just remind ourselves of what compound A is. So this is our structural formula for compound A. So we don't have to scroll up. So this is compound A, and we said that that was ethanol. Then we have compound B. Oh, this is compound B, and both of them are going to react now to give us compound C. So B, we said, is an acid, a carboxylic acid, and A is an alcohol. Now, when alcohols and carboxylic acids react, we end up with what we call an ester being formed. But there's when we're drawing the product, the ester, we have to draw the acid portion first. So let's just look at how the joining take place, or how the reaction takes place. I'm going to use black to show that it's the OH. We have to line up the OH from the acid with the H from the alcohol. And that will come off, that will be eliminated as water. And then in the middle now, we're going to get our C double bond O with a bond, which is the ester linkage. So let us now write the final product. We're going to start here on the left, starting with the acid. So we're going to draw CH3, that's the first portion, CH3. Let's put on the hydrogens as we go along. Then there's a CH2. Then we're going to have the C double bond O. And then after the C double bond O, the OH would have been removed. And this part here is going to be joined with the O up here. So we're going to have C double bond O. Then we're going to have an O. And this is where the blue comes in, because we're now in the alcohol territory. So this is where we are now. So that's the O. Then we'll have CH2. And then the last part of the alcohol will have a CH3. They asked us to draw it. They didn't ask us to name it. But for practice, we could name it. We always name the alcohol part first. So we draw the acid part first, but we name the acid part last. So we'd name the alcohol part first, and we'd name the acid part last. So just for practice, this is, the name would be ethyl. Okay, let's be consistent with our colors. So this would be ethyl, and the acid portion would be propanoate, coming from 3 carbons. Propanoate, ethyl propanoate. Check. We answered part 4 a while ago. in saying what compound A and compound B reacted to form. So it's an ester. And we said these are responsible for the lovely fragrance that we get in flowers. So it belongs to the esters. And they said that we should state two other types of reactions that compound A can undergo. So compound A, just a reminder, compound A was ethanol. So ethanol reacts, or alcohols on a whole react with organic acids to give us esters, right? So there are other reactions that alcohols can undergo. They can undergo combustion reaction, where they burn to give us heat, carbon dioxide, and water. And they can also undergo dehydration. So we can dehydrate our alcohols to get the corresponding alkenes. And just like that, we would have gotten 15 marks. So I hope you're putting in the practice and you're seeing the patterns. All right, so question number 4. You're provided with two identical samples of white powdery substances labeled D and E. One sample is finely ground sodium chloride and the other sample is finely ground diamond. Describe one simple test including the observations which could be used to distinguish between D and E. Now, in the early part of chemistry, when you're looking at structure of solids, we learn about diamond, the structure of diamond versus the structure of graphite versus the structure of sodium chloride. There's a nice table that outlines the differences. Now, it's good to commit those to memory, but it's even better to be able to apply, the knowledge there to be able to, solve a problem. And this is a popular lab that we normally look at. We're given different substances and we try to identify the structure of the solid based on the observations we get when we test them with, say, we test for their solubility, we test for their conductivity if the solid actually dissolves to form a solution. So we look for things like solubility in water, solubility in organic solvent, and so on. But for this one, we want to distinguish between sodium chloride and diamond. So we're just going to get straight to the point. So to sum of the compound, of course, we would get these compounds, the two compounds in separate container. We would add water. So let's get right into it. To some compound, we would add water and stir, not shaken, or is it shaken, not stirred? All right, so and stir. All right, sodium chloride, so NaCl will dissolve, and that's all we need. NaCl will dissolve, diamond will not. So sodium chloride is an ionic compound, so it would dissolve. Of course, diamond is a giant covalent structure, so it would not dissolve. And a mistake that students tend to make, we tend to say melt instead of dissolve. Now, melting has to do with a change in state when enough energy is applied to break the forces of attraction holding the particles together in the solid state. That has nothing to do, or that is different from dissolving, which has to do with dissociation due to interaction of the particles of the substance with the particles of the solvent. So we need to note that. So that is that. In this section now, part 2, we're to sketch a unit of sodium chloride, and this is for 3 marks. Now this is where we will draw the 3-dimensional structure of sodium chloride. And of course, many of us we tend to be perfectionists. And as I said, the word perfectionist, my lines are getting a little wobbly. We don't need to be thinking about technical drawing and isometric projection. We just need to be able to draw the cuboidal structure we need to show that because we would get a mark for that. So we need to ensure that we have our cube. So we're just showing 3 squares here. They are not really drawn to scale. So we're going to now connect lines across the faces. Right. Front, and then one here, and from the back, coming around there, we're at the back. Okay, so for the, we need a line coming down in the middle. I'm going to use broken line for that. We need one going across as well. We need one coming this way to the front. So we'll get a mark for the cuboidal structure, that's for sure. And we'll also get a mark for showing the alternating arrangement of the chloride and the sodium ions. So I will put in the chloride ions first. We'll put them at the vertices. So that would be chloride, and I'm just going to use size to distinguish. So that's chloride at the vertices. Each vertex has a chloride, and then we put in sodium, the smaller one. Sodium. So that means we would have chloride in the middle at the top. We would have sodium here, chloride here. We would have sodium here, chloride here, sodium, chloride, sodium, and we can go in the middle. We would have sodium in the middle. At the back we would have chloride, and it's probably getting a little confusing now, but we don't want that. So you would get your marks for this, the cuboidal arrangement. You would also get the marks for showing the alternating arrangement of the sodium ions and the chloride ions, and then you get 1 mark for labeling. So I would just label, this is the chloride ion, this is the sodium ion, right? Show them that we know what we're talking about. A plus bracket Cl minus, and just like that we would have earned, that's 5 marks, right? So I'm going to also post the link for a video that shows you how you could draw this, so you could perfect it. We're not saying this question will come, but it's a good concept to understand. So this is what the perfect one looks like. But as we said, we're not really aiming for perfection. We want to do enough to get our full marks, and we don't want to waste time on a question when we could be using the time to do something else. So sodium bonding with chlorine to form sodium chloride. Sodium is a metal, chlorine is a non-metal. So we know that this is an ionic, the type of bonding here is ionic bonding. And we just put full stop, argument, done. And we move right along. Now, here you're required to make predictions of properties of unknown elements based on their position in the periodic table. So, magnesium, calcium, and the unknown element X react with water. Now, students tend to, when they get a question like this, they tend to try to decipher or figure out what X is, but you're not asked to figure out what X is. It doesn't matter. It could be Jamaicanium, it doesn't matter. That doesn't exist as yet, but I'm sure somebody from Jamaica will discover an element and will call it Jamaicanium, right? So it doesn't matter what it is though. We just want to work with what we're given. It's in group 2, so we know that these elements are all in the same family. So they are going to react similarly. They're going to have similar chemical properties. So we also know that reactivity increases down the group. So these are some of the things that should be going through your mind when you see something like this. But to actually focus, we look at what the question is asking of us. They want us to discuss the relative reactivity of magnesium, calcium, and X with water. And we just want to be really plain and, you know, simple about it. We don't need to write to fill up all the lines that's there. We just want to communicate effectively and, you know, use our time well. So we could state, as it relates to reactivity towards water, we could say, we know reactivity increases down the group, so X is the most reactive, so we'll say X is greater than, or the reactivity of X is greater than calcium, whose reactivity is greater than magnesium. And there we've written a little reactivity series for these three elements towards water. That's it, 2 marks. Next, write a balanced chemical equation for the reaction between water and the unknown element X. Now they're all families, they're in the same group. If you know the reaction for one of them with water, calcium with water, you know the reaction for all of them with water pretty much. So in this case, we're going to write X and we put our state symbol there. It's a solid, very important. It's reacting with water, which we know is a liquid. This is going to give us the hydroxide. Of course, X is in group 2 and the hydroxide radical, or the hydroxide ion, is OH minus, so we would need 2 of it. So that's X2 plus to go with OH minus. 1 minus, of course, the charges are not the same. So we just look at finding the LCM. 2 into 2, 1. 1 into 2, 2. So this tells us we're going to need 1 of X, but 2 hydroxide. And of course, we put our bracket there to keep the group together. OH minus is a group. We call it a polyatomic ion or a radical. So if we're going to show that we have more than 1 of it, we have to actually put a bracket and a little subscript 2, which tells us how many of the entities we actually have present. So this is hydroxide of something in group 2. All hydroxides are insoluble except those of sodium, potassium, and ammonium. So it means that this, we would write it as a solid. And then we, of course, write hydrogen gas, which has to be written as H2. It ends in gen. Anything ends in gen, that ends in gen or ene, they're diatomic. So hydrogen, you write that as H2. And of course, you're going to balance, check to ensure that you have the same number of each atom on the left-hand side as on the right-hand side. So here we are, LHS is the left-hand side, RHS is the right-hand side. So we have 1x, 1x good. For hydrogens, we have hydrogen, we have 4 on the right, but 2 on the left. So we put a 2 here, we put a 2 in front of the water to ensure that that checks the hydrogen. So we now have 4 hydrogens, yep, and we now have 2 plus 2, 4, 2 oxygen, 2 oxygen, so balanced. So that's that. So on to the next question. Suggest a formula for this compound. Wait, I'm going too fast. Element X reacts with oxygen to form a stable compound. Suggest a formula for this compound. And I like this. Element X is in group 2, so when it reacts, it will form X2 plus. And we know oxygen, when it reacts, it gives us the oxide ion, which is O2 minus. So this compound is stable compound, and this is good. Will be a hug and a kiss. XO, XO, XO. Alright, XO is fine. Now, state whether an aqueous solution of this compound would be acidic or basic and give one reason for your answer. Now, the first thing we're going to do is state if it's going to be acidic or basic. There are several ways to approach this. Seeing that, well, one, we know that the group 2 elements are known as the alkaline earth metals. So it goes without saying that, you know, when they form oxides, those oxides would be basic. So we're going to state first that it would be basic, and we want to also give the reason. there's another reason we could use. All right, so we know that all metal oxides, we should say, all metal oxides are basic oxides except those of lead, aluminum, and zinc. Now, element X is in group 2, it's neither lead, aluminum, and it's not zinc. So there are several ways to approach this. So we could state, okay, we'll say group 2 metals are called so it's a group 2 metals are called alkaline earth metals. So their oxides are basic, or we could say all metal oxides are basic except those of lead, aluminum, and zinc, and we're good to go. And then for this one now, the last question here says, state one test to determine if an aqueous solution of this compound is acidic or basic. For 1 mark, we don't want to over answer or spend precious time that we could be using working on another question. After all, after we get full marks for this part, it doesn't mean that if we answer exceptionally, it's going to be spilled over into another question. So we just get straight to the point. So we could test the solution with an acid-base indicator like litmus, or we could use universal indicator paper or universal indicator solution. All right, we could also use a pH meter, but as we said, we don't want to over answer. It's just 1 mark, so we just get straight to the point. And you could compare your answer with what we have. Share in the comments. Let us know what you think, so we can know how we go about, working more, so you can actually benefit. This question is on organic chemistry, introduction to homologous series and reactions of organic compounds. Part A. Methane is the first member of the alkane homologous series. 1. List 3 general characteristics of a homologous series. They have the same general formula. They have the same functional group. They also have the same ending name. Part 2. Write the molecular formula of the second and third members of the alkane homologous series. So they've given us the first one, methane. So they want ethane and propane. So for ethane, the second one, it would be C2H6. And for propane, it would be C3H8. From this now, in part 3, we're asked to derive the general formula of the alkane homologous series. If you know it, you could just write it. But just looking at what we have here, C2H6 for ethane, C3H8 for propane, we're seeing that for the number of carbon atoms, we're seeing that the hydrogen atoms is twice the number of carbon atoms plus 2. So from that, we could write CnH2n plus 2, n representing the number of carbon atoms. 2 2's 4 plus 2, 6. 2 3, 6 plus 2, 8. Part B. 1-butene belongs to the alkene homologous series and exhibits structural isomerism. Part 1 of B. Define the term structural isomerism. This is the existence of organic compounds having the same molecular formula but different structural formula or different arrangement of the atoms in space. Let's get that down. Part 2 of B. Draw a fully displayed structural formula of 1-butene and its 2 isomers. All right, so we'll do 1-butene, and the 1 there is telling us that the functional group, which is our carbon-carbon double bond, is going to be found at the first carbon. Whether you want to count from left to right or right to left. But naturally, we read from left to right. So I'll put the carbon-carbon double bond at the first one from the left. All right, it doesn't mean that you couldn't put it on the first one from the right. So I'll put, so let's go. That's first carbon. That's a carbon-carbon double bond. But means 4. Let's adorn or put on the hydrogens on our carbons now. Each carbon must be taking part in 4 bonds. Carbon is tetravalent. Tetra means 4. Valence having to do with the valence electrons in the outermost shell. So that is but. That's 1-butene. And we could have also drawn it, we could have flipped it around, in which case the carbon-carbon double bond would be at, still at carbon 1, but from the other side, same thing. There we go. That's what it's the same thing. Same thing. So these two are the same thing. I just wanted to make that clear. All right, so let's look at an isomer now. So to get an isomer, we want to each time rearrange this so we get a new form. All right, and please look out. You can just check the card, the description above, for a video that will look at some of the common terms that are often confused, like isomers versus isotopes. So you can just check that out. If it's not there, you can just look back in a few days and it will be there. So just check that out. So we could take the carbon-carbon double bond and we could put it at carbon 2. And this is what the skeletal structure, the framework would look like. So carbon 3, 3 carbon, carbon 4. And again, we want to ensure that each carbon is taking part in 4 bonds. So there we go. So this is isomer 1. They didn't ask us to name it. Perhaps they'll ask us to name it in subsequent questions. And then we want to do isomer 2. So what we're going to do in order to get isomer 2, and I'm going to be using the one that I did in blue up top to illustrate. So we're going to let everything remain, but what we're going to do, we're going to cut off this portion right here. We're going to cut off this methyl group, and we're going to trade places with this hydrogen that's, let's call this carbon 1, carbon 2, carbon 3. We're going to trade places. We're going to take this methyl group, and by methyl group, I mean the CH3 group right here. We're going to take it and we're going to trade places with the hydrogen. And that will give us a new form, same molecular formula of C4H8, but the atoms are arranged differently in space. So when we do that, this is what things will look like to give us isomer number 2. So this is what we would have. So let's put on so this is in the middle, carbon 2. We're putting on the methyl group. So that's CH3. We're going to just draw it out, all fully displayed. And we swapped places with the hydrogen. We're putting that back on. And we just need to put the 2 hydrogens on this carbon, and we are good to go. Right? So 1 butene, 2 butene, and 2 methyl propene. All right. Part C will remain in few marks to make it up to 15. 1 butene, like all alkenes, are described as unsaturated compounds and undergo hydrogenation reactions to become saturated. Define the term unsaturated. So unsaturated means that there is a carbon-carbon double bond, or unsaturated means that the compound doesn't have carbons that are only taking part in carbon to carbon single bond, or carbon to carbon single bond. So unsaturated, let's just get that down. Part 2, state what is meant by a hydrogenation reaction. And if you look carefully, if you break down the word, you'll see hydrogen in the word and you'll see ation. So all it means is it's a reaction where hydrogen is being added. So it's so it's a reaction where hydrogen is being added to the alkene, and they want us to draw the fully displayed structural formula of the hydrogenation product of 1 butene. 1 butene. So let's just remind ourselves of what 1 butene looks like. Oh, this is not the answer. We're just reminding ourselves of what 1 butene looks like. So if we're adding hydrogen, then the hydrogen is going to be added across the carbon-carbon double bond. So we'd cut one of these bonds right here, which would now make room on carbon 1 and on carbon 2, or the hydrogen that we're adding. So the hydrogen, one of the H's would go on carbon 1 and one of them would go on carbon 2. So it would give us our final product, which would look like this. So it would move from an unsaturated compound to a saturated compound. So we could put a hydrogen here, we could put one here. They're all identical, but I just wanted us to be able to spot where it actually was added. So this is the final product, and that would give us the full marks. And I'm just going to highlight it by putting it in a box. So that's it. Question 6. Metal alloys are often used in place of metals because of their enhanced properties. Part 1. Define the term alloy. All right. So this is 1 mark. So an alloy is a substance that is formed when a metal is mixed with other metals and or non-metals. So it means that this metal can be mixed with a metal, this metal can be mixed with a non-metal. All right, so the common mistake we tend to make is to just think that an alloy has to be metals mixed together. All right, so let's get that in for our 1 mark. Part 2, name one alloy of aluminum and state its use based on one of its enhanced property. So there are 2 alloys of aluminum that we know, and we would have looked at this in a previous session. So we have duralumin. I think I worked on the pronunciation since the last time, and we have magnesium. So we're just going to work with one. So we're going to work with magnesium. It doesn't have as many enhanced properties as duralumin. So the enhanced property of magnesium is that it is resistant to, it's resistant, it's a T. It's resistant to check. So magnesium is resistant to corrosion, and as a result of that, now we can use this to make window frames, door frames, and roofing materials. It can be used to make window frames, door frames, roofing materials. Now, the other alloy, duralumin, it has more enhanced properties, a lot more enhanced properties, and therefore more uses. But I think in our previous session, we looked at duralumin. We just want to ensure that we learn other ways. So that one has, duralumin has low density. It's a very good conductor of heat and electricity, high melting point, good malleability and ductility. It's very strong and hard. So duralumin is probably the better one to revise or to practice or to study, because you have all of about 6 or so enhanced properties. So, the likelihood of you, if you forget 2 or 3, you still have 3 others. And then we have to be able to link the properties with the uses. So low density makes duralumin very good for aircrafts and car bodies. They're light, very good conductor of electricity, heat and electricity, makes it being able to be used as electrical cables and so on. It has good malleability, good ductility, so we can draw it into wires, hammer it into cans, bottle caps, and so on. So the possibilities are endless, but we just want to mix up the thing somewhat. All right, so just like that, we have 4 marks. Part B, a student conducted an experiment to investigate the reactivity of each of the following metals: copper, iron, zinc, and lead, by using solutions of their sulfate salts. The data presented in Table 3 shows whether a visible chemical reaction took place when each metal was added to the 4 sulfate solutions. And the key is there. Where there's a tick, it means that a visible chemical reaction took place. If there's an X, it means no visible chemical reaction took place. Doesn't mean that one wasn't taking place, but we use invisible or no visible chemical reaction to actually determine if one took place. Now, this might be hard for you to visualize, but you can check out the card above for a reaction or an experiment like this one. Similar. The only difference is that we did not tell you what the metal solutions were, or what the metals were. We call them metals A, B, C, and D. And then we had like the nitrate or the sulfate of the different metals. So this one is making it a little easier. They give you the metals. So with knowledge of the reactivity series, you can go ahead and just know what is supposed to happen. So you can check that out. The card is above. How I look at this or how I approach this, you can think of it as football. So we have the metals on our right and the metal solutions are on our left. So we will take iron, for example, and we add iron to a solution of copper sulfate. And if there's a visible reaction, which there is, the tick is there, it means that iron would be taking the place of copper. A displacement reaction will be taking place. All right. In our video, in our experiment, we call it the reducing ability of metals experiments. You can check that out. It should be helpful. It gives you color changes. You're able to actually see the visible chemical reactions as they occur. So from this one, the more ticks we see, then it means that a visible reaction is actually taking place. So let's see if we can interpret this. So when iron was added to copper sulfate, there was a tick to say there was a visible chemical reaction. When zinc was added to copper sulfate, a tick means a visible reaction took place. When lead was added to copper sulfate, it means that a visible reaction also took place. So everybody, all three metals here actually reacted with the copper sulfate or took the place of the copper sulfate. That's one way to look at it. We could also look at it going down instead of going across. So we could look to see how iron fared against all the other three, because we're not going to put iron with iron sulfate, even though when they did, there was no visible chemical reaction. So maybe it's best if we try to interpret the data going down. So we look at how well iron did. So if we're looking at iron, we look at if iron was able to displace or take the place of copper. Yes, it was. Was it able to take the place of, well, we wouldn't put it with iron. There's an X there for all of them. When iron goes with iron sulfate, zinc goes with zinc sulfate, lead goes with lead sulfate. So that doesn't really count. So it was able to take, there was a visible reaction with copper sulfate, iron and copper sulfate. There was also a visible reaction with iron and lead sulfate. So iron would have won for 2. All right. For zinc, there were 3. Zinc was able to, there was a visible reaction with copper sulfate, there was a visible reaction with iron sulfate, and there was a visible reaction with lead sulfate. And then for lead, there was only 1 visible reaction. Lead was able to displace copper from the solution of copper sulfate, but it was not able to displace iron or zinc. So we're now going to use this information to answer the questions that follow. So from this, based on the number of ticks, we can determine, before we even get into the questions, we can determine who the winner was. And it's like football. So the ones that give you, the one with the most ticks, that is the one that would be the champion. So the one that's in first place would be ZN, just as a guide. It has 3 ticks. It would have reacted with 3 of those solutions or displaced those metal ions from their solution. So zinc could be more reactive than the next one is iron. Fe had 2. So 3 wins for zinc, 2 wins for iron, and only 1 win for lead. And oh my, we did not look at copper, but copper had no win at all. Copper did not displace any of the other the metal ions from their solution, from the other 3. So please note that the trend that, I guess as a control mechanism, we added, the copper would have been added to copper sulfate, the iron added to iron sulfate, zinc added to zinc sulfate, lead added to lead sulfate, but copper did not get any tick at all. So it would stand at the bottom of the table. All right, no wins. So 3 wins for zinc, 2 wins for iron, 1 win for lead. and no wins for copper. So let us now bear that in mind and see what we're being asked a little further down. So just by jotting down our guidelines, so from the table above, we had said that Zn was the winner. Zn won 3 matches. Zn won 3 matches. Iron won 2. Lead won 1. And copper won 0. So we can use that now. All that we've deduced, we can now use that to apply to our question. State which of the 2 metals is more reactive, iron or zinc. Give a reason for your answer. All right, so from what we saw earlier, iron or zinc, we know that zinc is more reactive. And we could just look back at what happened when zinc played the match against iron. So zinc was able, there was a visible reaction when zinc reacted with, and I want to get that back. When zinc reacted with iron sulfate, there was a visible reaction. On the other hand, when iron reacted with zinc sulfate, the iron did not displace zinc. So we want to just make a note of that. So we'll say zinc is more reactive let's be more specific. Zinc is more reactive than, so zinc is more reactive than iron because zinc displaces, or let's not say zinc displaces, let's say zinc, or because, so zinc is more reactive than Fe based on what we would have observed from the table. Zinc is more reactive than Fe because there was a visible reaction between zinc and iron sulfate, but not the other way around. I want to use evidence that was in the question. Using the data in table 3 on page 22, deduce the order of reactivity of the 4 metals, copper, iron, zinc, and lead, from the most reactive to the least reactive metal. And I think we did that earlier. We said it's zinc. Zinc won 3 matches, iron won 2, lead won 1, and copper did not win any. So zinc is more reactive than iron, which is more reactive than lead, which is more reactive than copper. Part 3. The student recorded the following observations from the reaction between the iron and copper sulfate solution. Observations: reddish brown solid coating formed on the iron strip. Blue color of the solution changed to dirty green. All right. Account for the observation made from the reaction between the iron and copper sulfate solution. So let's, first things first. So the reddish brown solid coating that would be on the iron strip would be, so the reddish brown solid is copper metal, which are copper metal arising from Cu2+ ions being reduced as iron displaced copper. Iron 2+ in solution is dirty green. So iron, we want to say, we're trying to, well, not trying to say, we're saying here, so iron took the place of Cu2 plus in the compound. And they want us to write the ionic equation, including state symbols for the reaction between the iron and copper sulfate solution. Now, what the ionic equation is what is showing we normally call it the net ionic equation. It's what is showing what is really taking place at the atomic level. So straight up, this is what is really happening. It's just a transfer of electron process. So we would have started out with Fe, which is a solid. There is Cu2 plus aqueous. Or we could also add to the question up top or answer up top just know that copper 2 plus ion is blue in solution. So as it is removed or as it is reduced, the blue would disappear. But we don't want to over answer. So this is pretty much what is happening as we had started just now. So it's just a transfer of electron process. So the iron would pretty much be taking the place of the copper. So we would end up with Fe2 plus, which is aqueous, plus Cu, which is a solid. All right, so that's our final answer. Now, where is this coming from? We always show where this is coming from, or we arrive at this. So first it would be Fe solid plus CuSO4 aqueous to give us FeSO4, that's our iron sulfate, plus Cu solid. In the next step, we would break down whatever can be broken down into ions. So this is balanced as is. Fe would write it back, Fe solid. Copper sulfate solution can be broken down into Cu2 plus aqueous and SO4 2 minus aqueous. Iron sulfate, iron 2 sulfate can be broken down into Fe2 plus aqueous and SO4 2 minus aqueous. And copper we would get back as copper, which is a solid. So we would now go through and cross out anything that does not change in moving from the left to the right. We call those spectator ions. So we would cut out or we eliminate sulfate, they haven't changed. And then we check to ensure that everything else is, the charges are equal on the left side and on the right-hand side. So we had mentioned in a previous session that we call this the Bible technique because we balance the equation first, balance the chemical equation, we ionize, and after we ionize, we still balance, and then we leave out. That's where we eliminate anything that doesn't change in moving from the left to the right. And then we check to ensure that our charges are equal on both sides. So on the left side, the charge is 2 plus, on the right side, the charge is 2 plus. So this is what we write back, or we had at the beginning for our answer, but just demonstrating how we actually came to this point. All right, so that's the Bible technique for writing ionic equation. Over time, it becomes second nature. Part C. Some metal compounds are health and environmental hazards. Part 1. Identify which of the metals used in the experiment in B is most hazardous to the environment. So no doubt about it. Copper, zinc, lead, iron. The most hazardous one there, it goes without saying, is lead, Pb, or we could just write lead, spell it out, lead. And they want us to state 2 harmful effects of continuous exposure to the metal identified in C1 on human beings. All right, so ever since primary school, we've been hearing about the danger of lead pencil, the danger of lead being in paints, lead paints. And you know, we learned that many toy cars were recalled due to some harmful effects that the lead paint would have had on some toddlers or infants, some little children who actually scraped off the paint and ate it. So lead, we don't really want to come in contact with lead in the environment. Right, so we don't really want to be in contact with lead in the environment. So some of the harmful effects on human beings when we become exposed to them is mental confusion. That's one. It results in loss of cognitive ability. It can result in visual disturbance. When you move on to the medicine at university, you learn a little bit more about how these things actually happen. All right, it can even cause paralysis. So we'll leave it there. And they asked for 2, we gave 4. All right, so just like that, 15 marks, just like that. So please check out the other materials on the channel. There are several more sessions like these. There are experiments to back up some of the theory that is covered here. Please go through. If you find value, give it a thumbs up, share with your friends. If you haven't subscribed, subscribe. Consider subscribing and turning on post notifications so you will not miss anytime new material is added. So this was another session with Chem with Ken. Couple later.